Good morning. This is Dr. Bauer from Mercer University, Penfield College, and this is for the course Applied Statistical Methods, Math 220. And we're going to look at Chapter 1, the beginning material for statistics. So statistics is the science of planning studies and experiments, obtaining data, and then organizing, summarizing, presenting, analyzing, interpreting those data. So there's a lot of things we do in statistics, but it all has to do with analyzing data. And then finally, we draw conclusions based on the data. Now, in addition to doing statistics, we want students to be able to study statistics to understand statistics that others produce, not just to be able to do statistics yourself. So we want you to be able to realize when another person doing statistics is maybe not doing the best, having the best use of statistics, or So here's an example. If you look at the bottom of the screen right now, I asked the question, what is wrong with this graph produced from data obtained by America Online, AOL, and they had this survey where they asked people to respond to the question, have you ever been hit by a computer virus? So there are two things that you should be able to recognize is not good for this type of survey and analysis. So think about it. What are the things that would not be statistically correct procedure in either the way they got the data or what they're doing with the data in this graph? Okay, well, if you thought of the fact that this is a voluntary survey, this is, asking people, respond, give your answer to the question. This is purely voluntary, and so whoever wanted to decide to answer this, so they selected themselves whether they would be in the survey. That's number one, a bad sampling method. Okay. The second thing was, if you look at this graph, there's something fundamentally wrong with the graph. As you see, the bottom of the graph is at 40,000. That's violating a principle of how to make correct graphs. If you're going to have a bar graph like this, where you record how many said yes and how many said no, you need to start at 0. So the bottom of your graph should be 0. Okay. What this makes it look like is, if you look at the length of the red rectangles, you see that the first rectangle, the yes rectangle, is like 3 times longer than the no one. But actually, if you look at the numbers, the yes is less than twice what the no ones are. So it's misleading. It's a misleading way to make a graph to start at 40,000 instead of starting at 0. So some key terms and ideas in statistics we'll start off with. First of all, the population of interest is the group of individuals or entities or things. It could be plants that you're growing to test something. It could be countries in the world would be the entities, or it could be people, individuals. But it's some type of thing that you're interested in collecting data from and studying. That's your population. A sample is a smaller group chosen from among the population that you're actually acquiring the data for. Okay? If you want your data to best represent data that would be collected from the population, you have to take extra care to choose a representative sample, which means that your sample was in some way chosen so that it represents the population. All right. A census is an attempt to collect data from the whole population. And right now we currently have what's called a national census, but it's not truly a census, because a census should get data from every person in the country. And for the last several decades, we have not done that. We have used sampling techniques to choose some of the people to be included in the census, and we just think that that is a good representative sample for the whole population. Data are observations, but datum is a single data value. So datum is the singular, while data is the plural. And the sampling method is the procedure you use to decide which individuals would be included in your sample, how they are picked from the population. Now, in statistics, we use what was called statistical and critical thinking. This is a very key part of this class. How do you think critically and carefully about your whole process? So here's the whole process, or our approach to a statistic situation and how it should be done. First, we prepare and consider several things before we even start. We look at the context, like what is the type of data we're going to be interested in, what are the goals of the study or the goals of the survey. You need to know your context of what are the important, what's the overall picture of what you're doing. Now the source, that's important. Not the source of where we're getting the data, that's your population, but I'm talking about the person who did the study. Now that could be you, or it could be someone else who did the study, but who is collecting it? Are there any vested interests? Now vested interest means that they have something to gain from the results coming out a certain way in the survey or in the study. So if some company who's producing a product does a survey about that product, obviously they have a vested interest. Or the Society of Prevention of Cruelty to Animals does a study. Well, if it's about cruelty to animals, then you know it's probably going to have, they're going to have a vested interest in that study. Okay. The next thing is the sampling method. Did you use some type of random sample, or was there a poor method used that wasn't random and therefore the sample's not going to be representative of the population? And so that's a key question to ask. All right. Now, after you do all that thinking about how the study was done, or you were going to do the study if you're doing it yourself, there's a lot to prepare before the study. But after you do all that good preparation, you collect the data, then you analyze it. Now, analyzing it means you're going to first maybe create some graphs to visualize the data, get a good picture of what the data is doing. You're going to calculate some statistics or summary calculations that will help you summarize the data. Now, creating graphs and visualizing the data and calculating summary statistics, that's all called descriptive statistics. That's the first branch of statistics we'll learn. The second branch of statistics we'll learn is called inferential statistics, and that item number 3 there under analyze, apply statistical methods to investigate hypotheses. Hypotheses are where you think that something happened. So you're inferring, did it happen or did it not? And you're inferring something about the population based on a sample that you collected. Now, lastly, you conclude. You make your decisions, but you need to ask things like this. Does the data show trends or any surprising results not seen before? So when you collect the data, you look at it and look for any surprising results that you didn't see before? Are results statistically significant? What that means is it's unlikely to have happened by chance. We'll talk about that a lot more. Or do they have any practical significance, these results that you find? It might be statistically significant but have no practical significance. Practical significance means it's large enough to be meaningful or useful. If you're basing many multi-million-dollar decisions on this, you better make sure it's going to be meaningful or useful. If, for example, an educational unit such as a school district tests a new type of approach to education, and it's a very costly thing, then it better have significant results, not just statistically significant, but practically significant results. And then lastly, has data collection, interpretation, or final analysis been handled in a poor or in a biased way? When you look at the data collection and their final interpretations and decisions, were they swayed by their biases? So you'd have to think about those things. Now, there are several pitfalls mentioned in the text when collecting or analyzing data. First, you need to have a good sample, so it has to be representative of the population, but ones that are poor are ones that were either taken by convenience. You just went to one location and collected your sample of people by interviewing them on the street. That's a convenient sample, and those people who are there at that time may not or probably don't represent a wider group of, a wider population of people. Or a volunteer sample. The days of the internet, you can post some question on some site and people will respond, but it's called a volunteer sample because they're totally deciding on whether they're going to be selected in your sample or not. Another pitfall is having really small samples. 4 out of 5 dentists prefer brand X. Well, were just 5 people surveyed? How many were surveyed? It doesn't make it very valid if only a few were in the sample. Non-response. Now, non-response means that you've randomly picked a person and asked them to participate, but they didn't want to respond. They refused to participate. And that's getting more and more of a problem today. People, I don't know why, but they just are too busy or something, and they don't want to respond. If you've randomly picked somebody, you want to get that person's data because you're using the randomness of the selection. Reported results rather than measured results. Now, if you ask somebody how much do you weigh, especially perhaps women, or I don't know, maybe men are also just as affected or sensitive about telling their weight. I mean, you're going to have some variations between what's reported and what's reality. Okay, same as if you ask people, okay, how much did you spend on restaurants last year? Well, they're going to estimate, so it's going to be rounded. They're going to say $500 or $300 or whatever. It's going to be a rounded number, so it's not going to be very precise. So you're expecting them to report their results, and it's not going to be precise. Loaded questions or wording bias. You're always going to get more positive of response when you ask a question like, should Congress help the children by doing this? Or, you mention the word children in a question, you're going to get a more positive response because everyone wants to help the children. Okay, so it's a wording bias. Or if you ask a question and during the question you give reasons, either for or against, why the person should respond in a certain way. So it's a biased wording of a question. The order of a questions in order of items in a question could sway the results. Here's an example. When the words traffic and industry are switched in the statement, would you say that traffic contributes more or less to air pollution than an industry? When they ask it that way, more people say traffic. But if you switch the words around, would you say that industry contributes more or less to traffic? Then they say industry is the highest. So, you know, it totally depends on the order in the question. Precise numbers also often imply more accuracy than can be allowed. Like they might give a population of the United States as 323,147,826 people. Exactly that. You know, that's more precision than is allowed. I would just give a population to the nearest million, maybe million and 100,000, but no closer than that, because there's people all the time that are entering the United States or leaving the United States or being born or dying in the United States. That those numbers are always changing, so you can't be that precise. Okay, so when you have two numbers and maybe you divide one by the other, don't carry it out to as far as the calculator gives you when you divide. Think about a little bit of precision. Give me another few digits beyond what the numbers in the problem were, but don't carry it out all the way. That's too precise. Also, percentages can sometimes be used incorrectly. When there's an example given where the Continental Airlines claims 100% improvement in their baggage loss department. 100% improvement. Now that would imply that no bags are lost. No suitcases are lost, which is obviously not correct. So there's also on page 11 in the textbook examples of converting between percents and fractions and decimals. You need to be able to do that for statistics. So study that if you're a little bit, uncertain about that. And then misleading conclusions about the data, such as thinking correlation implies causation. If both X goes up and Y goes up at the same time, does that necessarily mean that X caused Y? No, it doesn't necessarily. It does, just because one is going up as the other one's going up does not mean one caused the other. We'll talk about that later. Now, there's some textbooks mentioned at the bottom of the page that talk about various pitfalls or misconceptions or confusing things about statistics, way people deceive other people using statistics, and you can look at those three books, to study more about that. Now, section 1-3 discusses the types of data. What are the types of data that are, that you can collect and do calculations with statistics? Now, the first category or the first type of data, you can't do statistics with it at all, because the categorical or nominal data is data that serves to simply classify individuals into groups such as male or female. So if you're writing down the sex of the person, male or female, that is qualitative data. Or it could be some label to describe a certain characteristic or quality. without any numerical measurements that measure how much of the quantity. This is also called qualitative data. So an example is the political affiliation of the person. So are they Democrat, Republican, Independent, Libertarian? So that is called categorical or nominal data. All right. Now sometimes numbers may be used in categorical data. Numbers are used, but they're purely for identification purposes and do not measure anything, such as ID numbers. So your Mercer ID number, that is data, but it's not quantitative in the sense that it doesn't measure anything. It's just identification. Okay, so you could still consider that categorical data because it's just numbering the students of Mercer. Same thing with team jersey numbers. They're purely for identification, and you wouldn't do any calculations with the jersey numbers. Okay. Now, let's talk about quantitative data. So we'll distinguish two aspects of quantitative data. First of all, these are not the different levels of quantitative data, but just two aspects of them. Whether the data is discrete or continuous. And then we'll also talk about the level of measurement on the next slide. Now, quantitative data is said to be discrete when the number of possible values is finite or countable. Now, finite means they stop. So 17 or 39, that's a finite number. It stops. It's not like infinity. Now, countable means the number of possible values can be counted, although it may take a very long time to do so. So here's an example. The number of books you have. Now, that might take a long time to count if you have a lot of books, but you could count them. Or the number of rolls of two dice. You got two dice in your hands and you're rolling the dice, and you're going to see how long or how many rolls it takes before you get double sixes. Now, theoretically, you could just go on rolling and rolling and rolling and rolling, and it never doesn't seem to ever reach, getting those double sixes. You could just get so unlucky that you're never going to get double sixes. But still, you could keep counting and finally, get the answer to that question. So that is called discrete. Okay, either finite or countable. Now, quantitative data that's continuous, when the number of possible values is infinite but not countable, such as data on a continuous scale, like the lengths that could be measured with a meter stick. Now, a meter stick, you have a certain, length that could be measured with that, but it's all the numbers along that scale. 2.59 inches, 3.72 inches, 5.7193 inches. There's just an infinite number of measurements along that continuous scale. So that's called continuous data. The time it takes to run a race. You get your stopwatch out and you're measuring the amount of time. Well, that's on a continuous scale. If your stopwatch could measure in hundreds of a second or thousands of a second, you could have theoretically, infinite number of possible numbers the time it takes to run that race. So that's called a continuous data. That's assuming always that scale can be subdivided indefinitely or infinitely subdivided. Now here's an example of the two. The number of cans of soda that you open at a party, that could be discrete because it's only going to be a certain number of cans that you've opened. 29 or 32 or whatever the number. But the amount of soda you drank, you or your party drank, would be continuous because some people might leave a partial can they didn't drink that, and so it could be any number between 0 and the highest possible amount of soda that you can get out of those cans. So it's a continuous number because you could measure volume of soda, you know, any amount, 3.926 ounces, or 13.5917 ounces. So it's a continuous scale in terms of the amount of soda. Now, the levels of measurement for quantitative data, this is only, well, I'm sorry, for all kinds of data, are the following. These four you need to know. The nominal level of data, same as categorical, consists of names or labels that classify individuals into categories. Now, we've already talked about this. This is the same as qualitative data. So nominal data, categorical data, same as qualitative data. But where there's no ordering scheme, you wouldn't order, which one goes first. Independents, Republicans, Democrats, Libertarian. I mean, you're not going to put them in any order of importance or whatever, male, female. There's no order in particular. So nominal data is just categories and there's no order scheme. Now, ordinal data can be arranged in some order or ranking, but where differences obtained by subtraction cannot be determined or are meaningless. Okay, now class rank, first in the class means they've got the highest grade point average, so valedictorian, second in their class, third in their class, fourth in their class, fifth in the class, etc. Class rank is ordinal level because you can put them in an order, but it doesn't make sense to subtract. You can't go, oh, okay, the fifth place minus the second place is 3 places, and that has any meaning. That has, subtraction is meaningless. Here's another example. Small, medium, large, and extra large. So this could be, size of drinks at a fast food place or size of t-shirts, but that's ordinal level because there's an order to it: small, medium, large, and extra large. But you wouldn't do any subtracting with that. Well, what's the difference between a small and a large? That has no meaning. Okay, now interval level data can be arranged in order and differences are meaningful, but there's no natural zero or starting point at which none of the quantity is present, such as test scores. Now, test scores, you can, different test scores, you can arrange them in order, and the differences between them have meaning. Johnny got 20 points less than Susie. That we can subtract, and that makes some sense. But you can't really say with test scores that 0, if the person gets a 0 on the test score, that means nothing, as in they knew nothing about that topic. Okay, I wouldn't ever say that a student who gets a 0 knew nothing about it. They just didn't answer the questions correctly by chance, or the questions that were asked they didn't know, but they knew something. Okay, so since there's no meaningful 0 where nothing of the quantity is present, then you can't form ratios where you say one student knew twice as much as the other or something like that. Now, IQ scores are an example of interval data. 120 does not represent twice the IQ of a person with 60 IQ. It doesn't work that way. So you don't, talk about one person doubling the other person and what that means, okay? So interval level data is where you have a scale. It's an even scale that you're measuring on, but there's no 0 mark on the scale that has any meaning. Now, ratio level data can be arranged in order, so there's an order to them, just like ordinal. The differences are meaningful, just like interval data. There's a scale, so you can do differences. And there is a natural zero or starting point at which none of the quantity is present. So for data at this point, differences as well as ratios between values are meaningful. So if I ask you, what's your income? All right, so some people might say I make, 40,000. Some people might say, oh, I make 80,000. Now that makes sense to say one makes twice as much as the other because zero is meaningful. A zero income has a meaning. The person did not make any money. Okay. Now weight and height, even though I know a person can't be zero weight or zero height, still we do have a concept of what zero weight or zero height is. It's, nothing, no weight on the scale, or no height above wherever the bottom point is. So zero does have meaning on weight and height scales. So then any giving the weights or the heights of a person, that's ratio level data. Okay. Now in addition to what we just already talked about, we talked about qualitative or nominal data. We talked about quantitative data in the form of ordinal or interval or ratio data. There also is, when you start doing calculations, there's two terms, a parameter and a statistic. Now, a parameter is a quantity that's associated with the whole population. It's associated with the whole population of interest, such as the average weight of all women in the United States. I'm sorry, average height, I meant to say, of all women in the United States, or the average glucose level of all newborn babies. So we have a hypothetical population. We don't really know how many are even in the population exactly, but we have this, what's called a parameter. It's a quantity that we're hypothesizing about, in this case, glucose level of newborns, for example. So unless we know all the values for the measurement of all members of the population, we cannot calculate this parameter, although we may discuss the quantity theoretically. So a parameter is a number that is associated with the whole population. And most often, we don't know what it is, but we just want to talk about it and figure out something about it, try to estimate it. Now, a statistic is a quantity that describes the population or has been calculated from data obtained by individuals in the sample. Thus, it is often not exactly equal to the parameter, although it may be close, ideally. So let's say we have this glucose level of newborn babies parameter. So we take a sample. We collect the glucose levels for 30 babies, let's say. Okay, we measure their glucose levels, and then we get the statistic, which would be the average glucose level for all those 30 newborn babies. So that is a statistic because we calculated it from the sample. All right. Now we hope that it's similar to the parameter of glucose level for all newborn babies. Okay. We hope that our sample represents all glucose levels of newborn babies. Okay. But we're not sure of that. All right. Now here's an example. Maybe a possible quiz question or test question next week. A politician claims that 35% of voters will vote for him. Out of 200 polled, 30% say they would vote for him. Now, 35% here is considered a parameter because the 35% is speaking about all voters, possible voters. The politician claiming 35% is how many would vote for him. So that is just an estimate or guess by the politician. But that's called a parameter because it's referring to all the people in the population. Now the 200 polled, out of 200 polled, it says 200, those are your sample, that's your sample, and 30% said they would. So 30% is called a statistic that we calculated from the sample data. All right. Now notice here that the data collected was not numbers, it was yes or no, whether they would vote for this politician. So the data was qualitative or nominal, yes or no, all right? Even though we got a number from that, the 30% tells the what we call the proportion of yeses. 30% is, how many yeses divided by the total in the sample, all right? So it must have been 60 in the sample because 60 divided by 200 gives you 30%. Now, collecting sample data. Now, two types of studies in which data is collected. Okay, observational studies, where researchers observe and measure or collect data for characteristics of the participants or individuals, but they do not attempt to modify the participants to compare them with others who were not modified, not altered. Okay, there are not multiple groups where they do something to one group but they don't do it to the other group, or they treat one group differently than the other group. It's just everyone's treated the same. Okay, now they may do some treatment to see the effects of that treatment, but with an observational study, they're not treating one group differently than the other group. So here's an example. You survey a sample of single women to ascertain their average income. You're interested in how the single women are doing, so you anonymously survey and ask, about their average income, about their income. So that is just to collect the data. It's just observational. You didn't try to do anything with the women, all right? Now, experimental studies are studies in which some treatment is applied differently to two or more groups. That's the key. You got to have two or more groups that you're treating differently. Now, then the effects of the treatment are observed in order to compare the effects. Now, suppose you randomly choose 100 single women, 50 of which are given financial help while 50 are not. So that financial help might be advice, might be, some, monetary help, but 50 of them get the financial help, 50 do not. So after 2 years, you come back and you talk to the women and find out their financial statuses of those who received help, and you compare those with those who did not receive help and see how much, after 2 years this has helped, or if it has changed the financial statuses of these women. Now that is an experiment because you're treating one group with the financial help and the other group is not receiving the financial help. Okay, so I hope you see that distinction. Now, as we said, a lot of statistics, it has to do with finding a good representative sample. The best way to create a representative sample is to make sure that every possible sample of a particular size has an equal chance of being chosen. Now that right there is a mouthful. Okay, you're trying to make sure every possible random sample of a particular size has an equal chance of being chosen. This is called a simple random sample. So one way to do this is to write the names of all the members in the population. You got to be selecting them from the population and put them in a hat and draw out 10 names out of that hat. So we're assuming a population that's not too large. Here, all possible samples of 10 have an equal chance of being chosen. Every possible sample of 10 names there could be chosen just as equally as some other sample of 10. That is a simple random sample, okay? Now there's some other methods of choosing a sample that are called just random, not simple random sample. They're just called random, all right? But they're not simple random samples. So here's an example. Suppose you've got 5 men and 5 women in a company, okay? You're going to flip a coin. You're going to choose 2 people from that company. But you decide to flip a coin to choose the gender. So let's say heads, it's a female, tails, it's a male. So you flip the coin to decide the gender, and then you put the names of the 5 from that gender in a hat and draw 2 of them. So let's say you flip a coin and it comes up heads. So you take the 5 women and you choose 2 of them. So you put their 5 names in a hat and draw out 2 of them. So that seems to be a fair way of doing it. That seems to be a random way to do it, because you're flipping a coin to decide the gender, and then you're choosing 2 out of the 5 in the hat. The problem with this is that not every group of 2 people could be chosen. It is true that every individual person has an equal chance of being chosen, so we call this random, but not every sample of 2 has an equal chance of being selected, since a pair consisting of different genders would be impossible to choose. Because you flip the coin and you either are taking all the males and then choosing 2 out of those males, or you're taking the females and choosing 2 out of the 5 females. So you're never going to get a sample where you have 1 man and 1 male and 1 female in your sample. Okay, so that makes it not a simple random sample, because not every possible sample of 2 people could be chosen. I hope you distinguish that. Now, some sampling methods or techniques that are either pretty good or somewhat good or not a good situation are listed here on this page. First is called systematic sampling. This is where you pick a starting point, some random starting point in a list, and then you're going to choose every kth individual, such as every 10th individual, every 10th participant. Okay, so it's like you open a phone book, and then you're going to take every 20th name that you see, and that's going to be your sample. Now that's called systematic sampling, okay, where you pick some starting point and then choose every kth name or thing. Or maybe a quality control guy or gal goes into a factory, and the bottles are going, let's say it's bottles of whatever, Pepto-Bismol, and the bottles are passing through, and the control person grabs a bottle, and then every 20th bottle they pick out another bottle, and they just keep doing that, and then until they got as many as they want, and then they'll test, is it okay, is it taste the same, or whatever they're testing. So that is called systematic sampling. Now, convenience sampling is a biased way and a poor way. It'll give you what's called a biased sample. Bias means shifted or directed to one side or the other, and it's a poor way to do it. It's picking individuals easily accessible for your sample. So you might go to Walmart and just stand in the parking lot and pick people there. Well, that's not going to be representative of everybody. Okay, not everybody goes to Walmart. So using your Facebook friends as the participants in a study or a survey, that's a convenient sample. Your Facebook friends does not necessarily represent other people in a population. Okay. Volunteer sampling. This is where you're allowing the individuals to self-select to be in the sample. So radios do this all the time. They say, okay, call in this number, here's the number, call in and give us your opinion. And so they get, 100 people to call in, and then they say, well, 35% said this and 62% said this. And, that is not a good way to sample. It's called volunteer sampling, and it's going to be a poor sample. Now, stratified sampling is a pretty good way. It's by subdividing the population into 2 or more subgroups, what we call strata, and then randomly choosing a sample of proportional size, usually from each. Okay, so here's an example. So let's say you want to ask people about police violence. Okay, police, using too much violence. Okay, so you know that this is a racially charged topic. So you want to get a sample of people, when you in your survey that represent the people in the country or in your state or wherever. So what you do is you go out and find the demographics in the country or in the state or whatever the demographics are, and you find out that, okay, so many percent are white, so many percent are black, so many percent are Hispanic, so many percent are other. And so you find out those percentages out there in the population. Then when you create your sample, you're going to take that same percentage in your sample to be, those different racial categories. So if 60% are white in the population, you want 60% in your sample to be white. Same thing for the other categories, racial categories, but that's called stratified. You're making sure that they're in the same proportion as in the population. Now, another thing is called cluster sampling. This is when you divide the population into sections or clusters, which may be existing groups. Okay, could be like counties of a state. There's like, I don't know, 100 and something counties in Georgia. Those are existing regions already that you could use. Okay, or it could be high schools or schools in a district. Schools in a district. So you do clusters. So you might choose a couple schools in this area, a couple schools in this area, but you're randomly choosing which clusters are going to be selected in your sample. Okay. They do this for the national census. They do a lot of cluster sampling. They randomly pick certain neighborhoods in a city area. Okay, they can't go to every neighborhood, but they randomly pick certain neighborhoods and they try to make it representative of people in general throughout the city. Okay, but then once they've chosen that neighborhood, they have to go to everybody in that neighborhood. It's not like they choose the neighborhood and then they choose just selected people from that neighborhood. All right, so anyway, now multi-stage sampling is when you're combining 2 or more of these methods. So here's an example. Suppose you use clustering and then you also use stratified sample. So you use clustering, but then you also make sure that the racial categories are all matching the population demographics. Okay, so there's an example of that. All right, now some things on observational studies. Now there are three types of observational studies. They're what are called retrospective studies, also called case control studies. These are looking back at past records. So they're not going to collect any new data right now. They're just retrospect or looking back at cases in the past. Now, cross-sectional studies look at current data from the subjects in order to take a snapshot, a current snapshot of what the situation is like right now. Okay, and then prospective studies or longitudinal studies, or also called cohort studies, they follow the subjects for many years and collect data for many years and try to investigate the changes that occur, or did these people that had this drug get disease or whatever. So they're looking at all the aspects but into the future, and they follow them for several years when they're doing their study. Now, I want to say things about some designing of experiments. Experiments we'll talk about later, but there's various principles that help you design an experiment. First of all, the principle of randomization. You need to make sure you use randomization to help make your sample be representative of the population. Okay, so a basic randomized experimental design would look like this in point number 1 here. You take an existing group, or it could be a randomly selected sample from your population that represents kind of a new group, and then you randomly split them up into group 1 and group 2. So you just put their names in a hat and choose half of them, or use some type of random way of deciding who's in group 1, who's in group 2. All right, so then you apply a treatment to one of them, and then you just leave the other one alone, or don't have a treatment for that. So you have a control, which is the no treatment, and then you have a treatment. Okay, now you could have multiple treatments if you had more than 2 groups. If you had 4 or 5 groups, you could have 3 or 4 treatments. But the idea is that once you have done the treatment, then you compare the data. You collect data from the individuals and you compare the results. Okay. Now, experiments, a good thing about experiments is that you can actually know if something was important or valid in your research. Okay. You didn't do it for nothing. You have you can draw some conclusions, okay, that this caused this. Now, the principle of replication is the idea that we want to have large samples. And part of the reason behind that is if you had just small samples, there could be major differences in the 2 samples. One could be smarter or taller or, more healthy than the other group. But when you have larger samples, it tends to cancel each other out. So in each group, you have some that are, tall and some that are short, some that are smart and some that are not smart, some that are, good health, some that are not. So the more you have in your sample, the more it's going to be balanced out, one sample compared to another sample. Okay, so that's called the principle of replication, and it shows it works over many subjects. And then the third principle is the principle of blinding or double blinding. This is where you don't want psychology to change the results of your experiment. So what you do is you keep the participants blind, not literally blind, but unaware of whether they received the treatment or the no treatment. Okay, now this is called the placebo effect, and a placebo is basically just a pill that does nothing. Okay, and what they found was that when you did a study and you gave a real drug to some and a fake drug, I mean, you didn't give that you didn't give a drug to the other, you had some real results, but then when you switched it around and then did not give the drug to the first group but gave it to the second group, the results were exactly the same, but it was, also it was found to be because of the psychological aspects, that when people know that they're testing something that might help them, they tend to improve just by that psychological effect. Okay, that's called the placebo effect. Now here's an example. My son was in a car accident and he had broken his leg in the accident. And so this doctor asked him, do you want to be in a study? I'll give you $100 or whatever if you participate in this study. Okay, and what it was some magnetic device that he would strap on his leg for about 20 minutes every day, and it was to see if the bone in the leg would heal faster with this device or not. And it was a large group of people, and there's two groups: the group that didn't get this treatment and the group that got this treatment. And they're going to see if there's differences in their healing of their legs or their limbs. Now, the thing is, my son didn't know whether he had the real device or a fake device. He would strap it to his leg and turn it on for 20 minutes, but he didn't know if it was doing anything or not. It weighed the same as the other device. Everything was the same except, the light came on too, but it didn't produce the magnetic pulses that the real one did, if that was the case, that he didn't get the real one. He might have had the real one. He didn't know. So that's called a blind experiment, when the participant doesn't know if he's getting the real treatment or not. Okay. Now, a double-blind experiment is when not only that, but the person's giving the treatment don't know whether they're giving the real treatment or not. So the nurses that gave him that device, maybe they didn't even know whether the device was the real thing or a fake device. That's called double-blind. Okay. Now the next situation or next principle is called control. The researcher tries to eliminate any confounding variables which may affect the dependent variable. And the way to do this is to ensure that, except for the independent variable, the groups used are about equal. So except for the treatment itself, which is your independent variable, then the two groups are pretty much equal. All right. Now this is done by using randomization for the two groups. So here's an example, what's called randomized block design. You form blocks, groupings, according to similar traits. For example, males and females. So this would be when the doctor wants to, let's say, give a new drug to try to help heart disease or try to help diabetes or whatever it is. And they know that men and women differ in that disease. Men have different heart conditions than women. There's various characteristics of the two. So they might first break it up into men and women. So those are called the blocks. And then after you broke it up into men and women, then you break up the groupings further, and you use randomization to decide if, which men go into control group and which men to go into the treatment group and which men go into the second treatment group, and the same thing for women. And then afterwards, you bring them all together and compare the results for the men and compare the results for the women. And then you also compare the results of men versus the women. And did the men achieve better results with this drug than the women, or vice versa, And so that way you can tell more from your experiment. Another situation is the match pairs design, before and after design. You have an existing group and you divide it up into 3 groups, let's say, group 1, group 2, group 3, and then you measure some quantity before, okay? Then you do the treatment or the control. The control would be nothing. You don't give them anything. You might do something to occupy their time, but you don't, give them the actual treatment that you're trying to test. But you measure before and after, and then you determine the change, the difference between the scores before and after. And then you look at that. So that's called before and after design. And another example is twins or matched pairs, pairs matched by similar traits. So in this case, you would go and have person number 1A and B, a twin number 1A and twin 1B. In other words, you got the 2 people that make up that the twins. But you put one of them in one group and one of them in the other group, and then you randomly decide which ones go into which group, whether they go into the control group or the treatment group. So there's some randomness in deciding which would go in which group. Then after that, then you look at the results between the 2 groups and see if the effect. Now, why would that be important? Well, twins have similar characteristics. So if you put one half of the twin group in one, like say in the control group, and the other half of the twin pair in the treatment group, then you're sure that they're pretty much identical in the 2 groups, and that's what you want. Okay. Now, the last thing is errors in statistics, types of error in statistics. Some errors are acceptable. We understand that there's going to always be this kind of error. So that's called sampling error or random sampling error. This occurs when the sample has been collected with a random or good method, but there's a discrepancy between the sample statistic and the true population parameter. And the cause of this is because in any sampling, you are randomly selecting who's going to go in the sample, and you have little sampling fluctuations or differences in the people that go into the sample, and that's normal. If you find, let's say, for example, randomly pick 10 Mercer students that are males, and you ask them, what's your height, and you get their height, and then you take another 10 and get the height of those 10 and average those. Well, of course, your first average is not going to be the same as your second average for the 2 different groups of 10 men. So you expect some fluctuations, okay? Now, the second type of error is random sampling error. This is a result of poor sampling, such as convenience or volunteer sampling, okay? So that is not a non-random sampling error. In other words, you did not use some type of random method, so your sample was, not representative and therefore poor sample. Now, a non-sampling error is the result of human error. So that's like the worst kind. It could include wrong data entries, computing errors, questions that have biased wording, false data provided by the responders, forming biased conclusions, or applying statistical methods not appropriate for the situation. So definitely all of those human errors are errors that you want to try to avoid. Okay. Now in section 1-5, I don't have a video for that, but I suggest you skim through the textbook section. It's about how do you use your calculator, your TI-83 or TI-84 calculator. And so look through that, try the exercises. All right, chapter 2 we'll look at in a little while here, but it's focusing on summarizing and visualizing distributions of data. So this is actually, doing things with our data by either visualizing or summarizing the data. We'll also create histograms, and we're going to consider measures of center. How do you best judge the center of a group of data? Measures of spread. Spread means variation, or how widespread the data is from the lowest to the highest values. The shape of a distribution. Is it a single mound comes up and goes back down, or does it have two mounds, or is it skewed to one side or the other? Is it trailing off one direction or the other? All those have to do with the shape of the distribution. And then we also want to talk about outliers, if you have any. That's the value that's extremely low or extremely high, and not close to the other values. And also we might going to look at time, as in changes of the data over time. So we'll take a look at that in chapter 2. Thanks.